to Maths 420, group representations of finite groups, and we'll be targeting basically on representation of groups. We end up using matrices. So let's see. Matrix representation is what we're starting with, okay? So the study uses the concept of linear algebra. You did that in 204, okay? So the concept of matrices will be used to see how to represent groups, okay? Finite groups, groups that you can count the number of elements in them, okay? We will need basic foundation in matrices. Your knowledge of 306 and 203 will be calling for even in this course, okay? So let's begin with those of matrices that you actually need for the course, okay? The first thing is to note that when you have a matrix of this form, you know it is written this way in large form, okay? So in short form, it will be written as this, okay? When the entry is A11 is simply I when I is equal to 1 and J equal to 1, okay? And if you happen to have another matrix, in the same way, you just write it this way, and its short form will look like this, okay? So that you need to remember. The next thing you need to remember is that if I want to add these two matrices, if I want to add A and B together, to add them together, to get a C, so C will be something like C, I, J. So to get a C, this is the rule. So you just simply sum the entries together, okay? So C would be this A11 plus B11 to get my first entry, right? For the big n by n matrix. So that would be like A11 plus B11 for the first entry, and on like that to keep going, okay? Well, if you're subtracting, you get, this is the standard rule. If you're multiplying by a scalar, this is what you get. If you're multiplying A times B to get a C, this Cij, this is what you will use. This is a standard formula. I will show you an example shortly with when k runs up to 2. So when it is running to n, this is the formula, okay? Simply note the first A, it's I, then K, then J for the B, and the A is IK, B is KJ, okay? Note that. If you're taking the transpose of a transpose, you get back the matrix itself. If you take the transpose of a scalar and A transpose, you get KA transpose, okay? If you are taking the sum, I think I should check this. One of you should check and verify. Send a message if you have gotten the correct, and if it remains the same. It's a little tricky right now. Okay, so if you're taking the sum of two matrices and then you took the transpose, that is the same thing as taking A transpose plus B transpose, okay? And then if you have AB, all transpose, the same as taking the transpose of A times the transpose of B. You need to know these things by heart. Now, if the inverse of the given matrix exists, then these identities hold. This one you see on the screen, okay? Once the inverse exists. I'm sure you know all of this, just that we just need to remember them. Now, like I was saying earlier, that I'm going to give us, for the general formula I'd written earlier for the product of two matrices, I will consider for a 2 by 2 matrix. So for a 2 by 2 matrix, C for A and this for B. I know you already did that in 101, and it was just straightforward, but there's a formula, and I'm sure you did that in 204. I'm not sure if you were shown the formula, but I believe that must have been done. But if not, this is a reminder of what to do. Well, so we know what C would look like. Instead of it going all the way to n, we're going all the way to 2 because they are just 2 by 2 matrices. And again, note the sum runs over IK and KJ for the B and A, like that. Okay, so what do we get? When I is 1 and J is 1 and K runs from 1 to 2, you get this for the entry for C11. Okay, so you know that means C11, I is 1, J is 1. So that's why you have that. But then K is changing from 1 to 2, remember, for the formula. Okay, so you get this for your first term. When I is 1 and J is 2, you get this. So you just simply run and check your values, your entries one by one. Okay, you just change because based on the I and the J entries. Okay, Same also, ij and k entry, k running from 1 to 2, like that. Same also, you can check, you can pause the video and verify that you will get this particular final answer. So pause the video, try it yourself and see. So again, the general formula for multiplying a and b, if it's m by n, and you well, n by n matrix, that's be n by n, because you'll be able to get the, it has to be a square matrix, that's the word. Okay, so how do you get the trace next? The trace of a square matrix. The trace of a square matrix is basically the sum of its diagonal elements. How do we mean to? This is how it is. So if you have a 2 by 2 matrix, you just sum this entries here together and you get the trace. So the trace is just a plus d. So basically what we're saying is if you're told to find the trace, you just write trace of a equal to, in our case it's 2 by 2 matrix, a plus d. So if you have the values, you just sum it, but we don't have the values for now because it's a general formula. Okay, let's move on. The next definitions and things you need to know, so we're going now, so everything I think you need to know about matrices is what I've given you at the previous slides, and now we're going straight into the definitions you need to know for representation theory. Okay, so for the first thing you need to know is what we call a faithful representation. So a faithful representation is an injective representation, okay? And while a linear representation is a function on G with values in K, and it's a function, remember, such that this holds, more like homomorphism, because it's an homomorphism actually. So if you can show that you take the homomorphism over x and over y, it's same as taking homomorphism over x and y. So for a linear representation, if you say A is a representation, you're simply saying if I take A xy, that's going to be the same thing as ax times ay. That's what we're saying. Okay, so the next definition you need to know is what we call an equivalent representation. What's an equivalent representation? If you have a representation ax, so it means it satisfies its condition, and there is a bx that you can write in terms of a, see a in terms of it, such that this t they are non-singular matrix. Okay, so if you can write ax in this form and well get a bx in this form, then a representation of G, then we say that A is equivalent to Bx. Basically, if you have A and B written in terms of Ax in this form, then we say Ax is equivalent to Bx written this way. Okay? The next definition you need to know is what we call the reducible representation. Now, Ax, the matrix representation Ax is said to be reducible over K if there exists a non-singular matrix, so that T that you saw in the previous definition, such that T runs over K and such that you can write this Bx in this form. But not only can you write in this form, you can write it in an extension as a matrix of this form, where Cx is an R by R matrix, Dx and S by X matrix, and this Ex in particular, note it, is an S by R matrix. And M, where is M coming from? You remember that Ax is a matrix, isn't it? So that's the representation. This is just telling you that it comes from a general linear group of matrices with M order M, okay? So M is going to be the sum S plus R. Once you have this, if you can represent Ax again in this form, precisely this matrix, then we say it is what? Reducible. Okay? Once you can represent Ax, this representation matrix Ax in this form, we say it is reducible. Okay, so let's continue. The next explanation is what we call complete reducibility. So a matrix representation Ax, you know what a matrix representation is? It is a matrix that satisfies this condition of homomorphism Ax, Ay. Okay, if it satisfies this that you see on the screen, it's a matrix representation. So a matrix representation over K is said to be completely reducible if Ax is equivalent to the diagonal of this listed matrices. They are sub-matrices okay, where the AIX are irreducible representations of a K. So you cannot break these small matrices anymore. Then we say they are what? We say that this representation AX over K is what? Completely reducible. So if you can write it to be equivalent to the diagonal of this matrices here, we say it is completely reducible. Okay. The next definition you need to know is what we call an algebraically closed field. What's an algebraically closed field? It's possible you already know this definition. So if you have a field K, it is algebraically closed if every polynomial equation of this polynomial, if it goes to 0 with its coefficients in the field, and it has a field K which has at least one root in K, then we say it is what? An algebraically closed field. Okay, so that's what an algebraically closed field is. We use all these definitions in time, but just know them for now. Next one you need to know in this chapter precisely is what we call the induced representation. Induced. You have seen the reduced representation. It was because we could write AX in terms of BX in a matrix that had CX, 0, EX and DX, if you remember. Okay, so now we have an induced representation. So AX takes this form, this very huge matrix you see on the screen. And note what happened to the B's. The B's are the entries in our matrix for AX, and AX is a matrix representation, remember? And if you want to write it in short form, you write it this way. Okay, so this matrix is said to be induced by the representation BU. What is U? U is an element in H. H being a subgroup of G, and thus it is called an induced representation. So it is induced because of this H, that is a subgroup of G, because the element in H are used by BU itself. BU being an equivalent matrix, if you remember, of the representation matrix AX. Okay, so then we have an induced representation. So please, you need to know these definitions, okay? And if you have questions during, you can post them on the WhatsApp group. Okay, so we begin with the first question. It's actually a theorem in your lecture notes. It's theorem 1.3. I have changed it into a question in the video here. So in your lecture notes, you see them as theorem, as statements, but I've converted them into questions here. So the question number 1 says, given that AX is a representation, so you know what a representation is now, it means that it satisfies our morphism relationship, right? Then we're to prove that for 1 in G, 1 being an identity element in G, that A1 will give us the identity unit matrix of dimension M. That's the first one. And 2, for X in capital G, that the representation matrix over X inverse is the same thing as taking the representation matrix all inverse. So we have to prove these two things, okay? So how do we do that? Let's start with the first one. So we're going to prove 1. Now we know that 1 is the identity element in G, right? We know that AX is a representation, meaning that AXY will be the same thing as AX. AY, right? That's what it means. Okay, so with that knowledge, we know that A1 should behave like the identity matrix, right? So that's what we expect, because 1 is the identity element of G. So A1 must behave like the identity matrix. So let's see whether it will do that. Okay, so since AX is a homomorphism, because it's a matrix representation, right? So for any X in G, this relationship will be satisfied because it satisfies homomorphism, right? Basically this. So we know this side, which is what we've written here, wherever there's X and Y, we've replaced it with 1. Okay, but then this is same as this is the same as this, right? So A1 becomes A1 times 1. But what's A1 times 1? That's just A1. Clearly, this would be the identity matrix, because we said already that A1 should have the behavior of an identity matrix. And automatically, we have proven the identity for the first statement, okay? So that's the proof to question number 1. Or should I say question number 1, part 1. Okay, so you can rewind the video and play it slowly. Play and go over it and try it yourself. Okay. The next proof for the second part, we're going to prove the relationship that AX inverse is going to be basically taking the inverse of the matrix representation. Okay. So now we know again that AX is a homomorphism. That is because it's a group matrix representation, right? So for any X. So this representation will be true, right? Because you know it satisfies homomorphism, right? So I'm supposed to have done AY, AX, AY. But because of where I am targeting to go, I have chosen to go by taking AX inverse. Because I know where I'm going. It's more like what we did in 306, okay? So now I know that AX inverse is going to be this by that condition of homomorphism. And we know what AX inverse is because we're working with a group. It's the identity in the group, which is the identity matrix 1. So therefore, this thing here is same as this here, which is what you have here. Are you seeing? Let's equate this to. And like what we did in 306, I'm going to multiply by the inverse of this because I want to show this. I have AX inverse in my equation already, but I don't have this. Okay, so let's see. So I have this already, like I was saying. We have this part. So we're going to multiply by the inverse of this, and definitely it has to be to the left-hand side of both sides. If I multiply the inverse of this on this side, I must do to the right-hand side, right? So I've done it here, I've done it here. So if you multiply this with its inverse, this goes to identity, right? This is what we have here. So it goes to identity, and we're left with just this, which is what you have here. And this times 1 is just this. So we've shown equality, okay? Proving the second statement. Therefore, both statements are proven, given that AX is a representation as required. Okay? So that is all to the first question, which again is a lemma in your lecture notes. The next question, which is question number 2 in the video on slide, is actually theorem 1.7. And it says, like I said, we phrased it into a question that if AX is a representation, we're to show that this one, this BX, written in terms of AX, is a representation. And we're told what T is any fixed non-singular matrix with coefficients in K. So what do? We want to show it is a representation, meaning we just need to show that BXY will be equals to BXBY. That's our target. So let's see how we go about it in this video as typed. Okay, I've tried my best to try and make it go along with your lecture notes so that you can put it side by side. Okay, so to show that this is a representation of G where it is fixed non-singular matrix, okay, we need to verify the group homomorphism property. So to show that, because we have to pick elements in G because they're all representation of a group G, right? We're trying to show representation of a group G. So we pick a G, and we know by the definition or by the question that wherever we see X, it becomes what? It becomes G. As you can see, G there. Okay, so we want to show it's a group representation. So if it's going to be a group representation, we need to satisfy this. I've chosen G1, G2 just to make it go with your notes because you could just as well have taken, say, another letter, but all of them must be elements in the group G, okay? So G1, G2. I want to show that we'll get this at the end of the day. Once it satisfies it, we're true. So the left-hand side is the left-hand side. So we have the left-hand side. Definitely to look like this, right? Because we know that it's going to be, BX was defined to be equal to T inverse AX T, right? So wherever we see X, we're putting BG1, G2. So G1, G2 replaces X. So that's why you're seeing that X, wherever there's X, this will be G1, G2. That's why it's right in the middle there. You seen it? You can take your time and look at it, and then you get it. Okay. So we know now that this B can be represented as this in terms of the T inverse AT. Okay. Now, since AX is a representation, we know that this AX will satisfy this condition, right? Again, you know what representation is, don't you? AX is a representation, meaning that AXY is the same thing as AX times AY. That's what it means. So it means that this our term here will split to this, right? I'm sure you've seen that. So in that case, this term, which is this and it's this, all of this, becomes the splitting. This thing splits, which is what you see right in here. Okay, so that's how I got this. I can simplify further. This has become this. So we're through with the left hand side. We go to the right hand side now. So I want to verify the right hand side. For the right hand side, next we need to verify the right hand side. The right hand side, let's see what right hand side was. So right hand side is right here. So this was our left hand side, which we had proven. We're now here, and I want to prove this and see whether it will give us the same answer. Okay, so let's see. So this is our right hand side, as seen in the previous screen, and we know what bx is. Again, bx is t inverse ax t, right? So now this is bg1. So wherever there is x, we put g1, right? That's why there's g1. You can see this term. It's just putting putting g wherever g1 wherever there's x. Okay, and then bg2, wherever there is x, we put g2. That's why you have this here. Okay, so our target is to simplify it and see if we'll get back this answer 4. We want to get the same answer. We want to see if it will give us the same answer. Okay, so let's see. So we've substituted, checked each one of them. Now this term here, right here, you can see if it disappears, this would look exactly like what we want it to look. Well, it will, because this is just T times T inverse, which is the identity matrix I. So T inverse AG1, AG2, which is exactly what we got previously. See, they're the same thing. So we're through with the left hand side. And so BG1, G2 is same as BG1, BG2, which satisfies the group homomorphism property. Therefore, we can conclude that BX in this form is a representation of G. And we're through with the entire theorem. Okay? So thank you. We'll be stopping here for today in this particular class. Questions can be asked, and please study the video towards our practical class. Thank you.